of a start on this, but we're going to get into a lot about why they're special, what makes them their own functional group. And in this particular chapter, we are going to look at reactions of side groups. We're not going to be talking about reactions of the actual aromatic compounds. So we've mostly seen benzene, but there are other aromatic compounds, so we're going to be focusing on in this class about why they're special and how we can determine if something is aromatic or not, and what causes something to be an aromatic class. So they do absolutely contain benzene and benzene derivatives, and those benzene and benzene derivatives are really our most common aromatic compound that we see. So we often will equilibrate benzene to aromatic compounds, but there's many other aromatic compounds that can be. The term aromatic comes from the fact that they were originally isolated from fragrant oils. A lot of essential oils have a bunch of benzene rings in them, but benzene itself doesn't actually smell very well, and a lot of aromatic compounds actually don't have a smell. Some of them just don't smell good, but a lot of them do smell very nice. Like, for example, benzaldehyde, which is benzene with an aldehyde hanging off, hence benzaldehyde, is what causes the almond flavor. So benzaldehyde smells really nice. They are really common. You see them in a lot of things like coal. When you heat up coal, you form benzene and benzene derivatives like naphthalene and toluene. So you see a lot of aromatic compounds there. They're common in a lot of pharmaceuticals. There's just some pharmaceuticals that have aromatic benzene rings in them. So you've probably heard of a lot of those names. So we're going to, of course, talk about naming, and there's a couple of different naming systems that we'll discuss that are accepted. Now we're really only going to talk about naming benzene. We're not going to talk about naming any other aromatic compounds. So as far as naming benzene, oftentimes benzene is a general parent name. For monosubstituted derivatives, once you have multiple substituted derivatives, that is different, but for monosubstituted derivatives, oftentimes benzene is the parent. So here we have chlorobenzene, nitrobenzene. Know the NO2 group, that's a nitro group, and that's how you name it, it's nitro. And here is, of course, ethylbenzene. Many benzene derivatives have common names, and the common names will often be used as the parent name if there's multiple substituents, so you do need to know them. So toluene is benzene with a CH3 group directly attached, and that's a very common one. You have to know that name. If there's, we have already looked at this one, if there's a benzene with an alcohol directly attached, that's phenol. Now remember, that has to have the alcohol directly attached, meaning the electrons and the oxygen are in resonance. This is phenol. This is not phenol. And this is not benzene at all. So you have to draw these correctly. Here we have anisole. That is when we have an ether with a benzene and a CH3 group. So instead of benzene, methyl, ether, it's actually anisole, and that's the common name and actually used a lot. Aniline is the benzene with a NH2 group directly attached. Again, that NH2 group has to be directly attached to the aniline. Benzoic acid is a benzene with carboxylic acid directly attached. Benzaldehyde, I just talked about that one. It smells really nice. It smells like almonds because it is what makes almonds smell like almonds. So the aldehyde is directly attached. Acetophenone, oftentimes that ACE group, and we'll see that in chapter 21 and 22 a lot as well. The ACE group, acetic acid, acetic anhydride, acetone is acetovinyl with a CH3. That's where that ACE term comes from. So when you see that acetovinyl with a CH3 directly attached, oftentimes it's named by that ACE. So acetic acid is this group, but instead of the benzene here, it's OH. So you'll see that ACE, so you might as well start getting used to it because, again, acetic acid is almost always named that way. It's almost never named by the IUPAC name. There are some common ones. And I tell you this because if you do take an MCAT or a dental exam or any of those, you'll see the ACE, you won't see the common name. So just recognize that. And then lastly, styrene, that's your benzene ring with a carbon-carbon double bond directly next to it. And again, it has to be in conjugation. If it's not in conjugation, it's not styrene. This is your starting material for polystyrene, which is the polymer where we have our polymer reacted through this double bond, and polystyrene is, of course, the polymer that forms styrofoam. So that's another one that's commonly used. So you do need to know those derivatives and you need to memorize them because they are often used as your parent names if you have multiple substituents. If the substituent is longer than the ring, then the benzene can be named as a side chain. And when it's named as a substituent, it's called a phenyl. It's not a benzo substituent, it's a phenyl substituent. And again, remember, this carbon is not counted as the parent name. It would be 1, 2, 3, 4, 5, 6, 7. So that would be your heptane. So phenyl-heptane. And you would need to name a locant number. You might see something like triphenyl. We are going to look at a reagent later on called triphenylphosphine, which is clearly a phosphorus with 3 phenyl groups. So when benzene is a substituent, it's phenyl. Here's an example of that. Now you don't know how to name the ketone, so I wouldn't expect you to be able to name this one. Oftentimes when you have multiple benzene rings, they get a little daunting to draw. So oftentimes they'll be drawn instead with pHs. The less common now, I don't see this terminology used as much, is a 5 sign. But I don't see the 5 sign used very much. The pH is used a lot more. So when you see a pH, that's a benzene. So this example would be tetraphenyl. And you wouldn't know how to name cyclopentane dienone because you don't know how to name a dienone yet. But that's okay, you will later. So here's another thing. Usually we use locant numbers, and that's still something you can use with naming, especially when you're naming based on the IUPAC. But there is another terminology that is often named for substituents. So when we have 2 methyl groups, that's xylene. But notice we can have 2 methyl groups attached differently. So in the first example, the 2 methyl groups are right next to each other. And notice, of course, that could be named 1,2-dimethylbenzene, or you see this terminology, orthoxylene. Here we have the 2 CH3 groups are on carbons 1 and 3. So that's 1,3-dimethylbenzene, or you might see metaxylene. And then the 2 CH3 groups being directly across from each other, 1,4-dimethylbenzene, or you might also see paraxylene. So what is that ortho, meta, and para? Well, that is a specification. If you have a R group, whatever it is, whatever that substituent is, the positions are designated in benzene rings, and this is only for benzene rings, really. Sometimes other aromatic compounds, but most commonly for benzene. So you won't see this with cyclohexane or anything like that. If the position, if there's something in the position that's on one of the adjacent carbons to whatever our substituent is, that's ortho. If we are at this position, that's meta, and then the directly across position is para. Notice there's 2 ortho positions. There's two meta positions, but there's only ever one para position. And that terminology is based on whatever substituent, when we're talking about naming, whatever substituent you're naming as the parent. So if you see in the orthoxylene, one of the CH3 groups are in the ortho position based off where the other CH3 group is, and then the meta and the para. So you will often see that naming, and that naming is acceptable. Sometimes you'll even see O, M, and P instead of ortho, meta, and para to represent ortho, meta, and para. And usually it's italicized, O, M, and P. So you're identifying your parent chain just like always. In most cases, it'll be the benzene or the benzene-containing derivative. Identifying and naming your substituents and assigning locus, and that can be the number, or it could be ortho, meta, para. Those are both acceptable. But again, ortho, meta, and para is only acceptable when you have a benzene ring. So if we look at these examples, our parent, because we have this CH-CO1O group, we have that aldehyde directly attached, our parent is going to be benzaldehyde. So our numbering is based on that substituent that names it benzaldehyde, meaning the aldehyde. So that is going to be our number 1 carbon, because that is the substituent being named for the parent. So that one should have the lowest locant number. So we can either name this 4-chlorobenzaldehyde, or it could be named para-benzaldehyde. Both are acceptable because this is the opposite position. So para-chlorobenzaldehyde is acceptable as well. So 4-chlorobenzaldehyde or para-chlorobenzaldehyde or p-chlorobenzaldehyde are all acceptable. If we look at the next one, we have that CH3 group directly attached, so that common name is toluene, and the most likely way it'll be named. So that's how you should name it. If we're naming it toluene, then this is our number 1 carbon because that's our parent carbon. That's where the substituent we're naming for is attached. So this can be 3-bromotoluene, or meta-bromotoluene is acceptable as well. And then in this one we have anisole, because we have that benzene ring and the ether with the CH3 group. Now anisole is only if this is a CH3 group. If this is an ethyl, then you're best off naming this as your ethoxy side chain. But anisole is only for this specific compound, benzene OCH3. This is anything that's not CH3, this is no longer anisole. So our nitro is hanging off. So we can name this one 2-nitroanisole or orthonitroanisole. We can also name this for the nitrobenzene parent, which could also be the nitrobenzene parent. And then this would be the substituent, so it would be 2-methoxynitrobenzene. Which is more correct? They would both be listed. If you were trying to buy this compound, you would see both names listed. So they're both correct. Neither is more correct than the other, and it's probably sold under both names. Sometimes that happens when you get more complex compounds in the IUPAC naming system. You do have multiple names that are acceptable. So both of these are acceptable, either this being your parent or this being the parent. Also, ortho. We could be using ortho instead of the 2. Let's look at this example. We see the phenol parent, so you should recognize the phenol parent right away when we've looked at phenol before. So that'll be our number 1 carbon, the carbon of the oxygen. Because if we name the parent based on that substituent, that's our number 1. Then we want our lowest numbering system possible. We have 2 bromines, so that's dibromo, and this can be 3,5. And either if we name it, number it clockwise or counterclockwise, it's going to be 3,5 either way. Notice, of course, we don't have any stereochem centers because we can't. These are all sp2 carbons, so we don't have 4 things attached to those carbons. You could also name this one meta-dibromophenol. That's also acceptable. Here's a compound that you will recognize the name once we name it, but you might not recognize it right away. Does anyone have any guesses as to what's the name of this compound? You've all heard the name. You know what this compound is. You might not have seen it, but you know what it is. So our parent, we see that CH3 group directly attached to the benzene. Not to name this one for the nitrobenzene because there's 3 nitro groups, so that one's kind of hard to name it as a parent for that. So the methyl is a better parent, so that's toluene. Anyone has a guess yet about what this is?
Yes.
Yep, it's exactly what it is. So we have 3 nitro groups, so it's trinitrotoluene. And of course we would put our numbers. And again, if we're naming for toluene, we're starting on that one as 1. So 2,4,6 trinitrotoluene, or as you know it, TNT, which is where the name comes from. So that's the most common way this one's named. You could also name it for the ortho and para, but because there's so many nitros, you probably won't see that one. The 2, 4, and 6 is much more explaining. So if we look at this one, M-nitrophenol is the best way to name this one. Not phenone. So our parent could be our phenol. So that'll be our number 1. Or we can say ortho, meta, and para. 3-nitrophenol would also be acceptable, though it's not given as one of the listing ones. But that would also be acceptable. Nitrobenzene, hydroxynitrobenzene would also be acceptable. The problem is we're not in the para position for this name. So if oxygen OH is our side chain, it is a hydroxy group, which is fine. So this could be hydroxynitrobenzene, as nitrobenzene being our parent, but we're still ortho meta to it, so it would be in hydroxynitrobenzene, and that would be acceptable. But p-hydroxynitrobenzene would be a different compound, and that would look like this, and that is not our compound. So this is not hydroxynitrobenzene. It's not nitrophenone because phenone is, this isn't a phenone. Now the ONE means ketone. We don't have a ketone. We name pretty well based on what we call the substituents. So even though we haven't learned about naming ketones yet, if you see an ONE, that's a ketone. It's a ketone somewhere in there. In this one, our best answer is going to be D. Here we do have a ketone, so that acetophenone is one of those parent names. And we have a nitro and a methyl. And we want our lowest numbering system, and because we're naming this base our parent, this is going to be our methyl base. So the lowest possible numbering system, in this case it does make a difference whether we go clockwise or counterclockwise, will be 3, 4. Because if we go the opposite way, it would be 4, 5. And remember, we want that lowest numbering system. So our lowest numbering system, 3, 4, is better. That's not the only way we can name this one. We could also name it as toluene or as nitrobenzene. And those are all acceptable. But typically, the more oxidized carbon, meaning the ketone, takes priority. But you'd likely see this one named multiple ways as well. It wouldn't, though, you wouldn't really see any of these named as a benzene as a parent, because once we have one of those common names, it's often named by the common name. So you should know those common names. So let's talk a little bit about benzene. Originally, it was postulated. We knew benzene is a ring of alternating double bonds, and it was postulated that we had an interconverting structure. But now we know a lot more about resonance, and what we know now is it's not actually an equilibrium process. We just have shared electrons between each of the 6 carbons. And it's actually in resonance not equilibrium, meaning we're not jumping back and forth. It's just that our average structure has all 6 pi electrons of the benzene ring shared between all of the p orbitals of the ring. So remember, it is different. We don't have an inner structure. So when you're drawing benzene, there's a couple of ways you could draw it. You can represent it as pH if you're not actually doing a reaction with the benzene. It's just hanging out. You all can see that. But the more common way is actually to draw it out. And you can draw it out, and either you show your 3 interconverting double bonds, or you can draw it with a circle in the middle. And the circle in the middle represents that we have 3 interconverting double bonds that are shared between all 6 p orbitals. Now what's not right is to not include all 3 of your double bonds. This does not react the same as this. So this is not benzene, this is cyclohexane. It's the chair structure typically. The carbons are not very reactive. We have no pi bonds. This is benzene. It's its own functional group. It's an aromatic functional group. So I will not give you credit if you draw this and you're supposed to be drawing this, because they're completely different compounds. They're not the same thing, and we need to represent them as such. But you can't show the circle, and the circle does represent benzene. It represents that we have that resonance structure. Basically, the circle is the average resonance structure. That's what you're representing. And oftentimes the circle will help us if we're trying to assess if we have stuff like symmetry. Because sometimes alternating double bonds kind of throw us off when we're doing a symmetry assertion, because we might say, oh, this doesn't have mirror plane because these 2 carbons have a double bond and these don't. But if we look at it with the circle, because the pi bonds are always shared between all 6, this actually does have a mirror plane. So sometimes we'll draw it that way so we can understand symmetry a bit better, which is important in the lab setting when we're talking about NMR and IR. So that's pretty important. Now, where is the stability coming from? The aromatic ring is super what we consider stable. And that's really why it's a specific functional group and why it has special reactivity. So if we recall that if we have a double bond in a cyclohexane ring, this is not benzene. If we react it with Br2, we can get an addition reaction. Pretty straightforward. We learned that since chapter 9. If we take Br2 and we react it with benzene, we're not going to get any reaction. Not if we just react Br2 with benzene. We need something else to get a reaction, and that's going to be chapter 19, and we're going to be focusing on that a lot. But right now, what I want you to just recognize is the difference in reactivity. This is why if you draw this with only 1 double bond and it's supposed to be this, and we'll mark it wrong, because they do not have the same reactivity, so they're not the same compound. Benzene doesn't react its pi bonds very easily. And unless if we add something else to Br2 reaction, we can keep this as much as we want. Eventually, we will degrade the benzene compound, but we will not force it to react with Br2 in an addition reaction. The products are just not stable. We can compare heats of hydrogenation to understand the stability of pi bonds. Remember, if we have a pi bond and we hydrogenate, having no pi bonds is always more stable than having pi bonds. Our completely unsubstituted cyclohexane is only really going to react with combustion, and we can do a radical bromination reaction, but otherwise we don't have any polarity, we don't have any instability, it's just not reactive. So cyclohexane is not reactive, we don't have any partial positive, there's no electrophile, there's no nucleophile, nothing. So that's going to be really stable. We see that when we have a double bond present, we lose about 120 kilojoules per mole of stability, which means that pi bond is reactive. And we can react it with stuff. Now we have functionality in that molecule. And then when you get a second pi bond, it's roughly double. It's not quite double, and the reason why this particular example isn't exactly double in instability is because I chose the 2 double bonds that are in conjugation. Remember, conjugation stabilizes the pi bond slightly, comparing 2 double bonds that are in conjugation versus not. Again, this is not benzene. So you would assume that with benzene, because we're now going to add a third double bond, that would roughly triple the instability. If one double bond gave us 120 kilojoules per mole of instability, and two double bonds about doubled it, you would think three double bonds would triple it. And that would be what's expected, but what's actually observed is that benzene is even more stable than having two double bonds. And that is not usually what we see with double bonds. So even though it's conjugated, something special is going on here. Because we don't see this if we're comparing, let's say, the linear structure. I don't know whatever happens to all the markers. Because this blue one's not working. But if we were comparing our linear structure, as we increase the amount of double bonds, even though it's in conjugation, we'd see a steady increase. So this is special. This isn't just because we have three double bonds in conjugation. There's something else going on to make it really stable. It definitely was unexpected when this was first observed. I mean, now it's expected because we call it its own functional group. But when this was first studied, this was absolutely unexpected. This was not what was predicted as a result. It's actually 152 kilojoules per mole more stable than what was expected. So we can use molecular orbitals to explain what's happening. And we're going to be looking at that, and again, you'll have to draw the molecular orbital diagram. However, with the aromatic rings, I won't have you actually draw the p orbitals with the nodes because it's kind of too complicated for the cyclic system. But you will be able to draw the diagram of where the orbitals lie. And I'll show you an easy trick for that. It's really simple. And it all has to do with, again, symmetry, because this is a mathematical representation. So it has to do with symmetry. So this is what our p orbitals look like. So remember, our molecular orbitals equal our atomic orbitals. So meaning how many atomic orbitals do we have? Now, just like when we looked at our linear systems, we're only going to be representing the unhybridized p orbitals. We don't care if there's things hanging off the benzene. It's not going to affect our orbital diagram. We're only looking at the unhybridized p orbitals. So we have a total of 6 unhybridized atomic p orbitals. So we're going to have a total of 6 molecular orbitals. But the difference in what our molecular orbitals are going to look like versus our linear systems is going to come in the fact that these 6 p orbitals are in a ring. So if you recall, and you just did a test on it, when we were looking at our linear systems, when we had our 6, and I'm not going to draw 6, our 6 molecular orbitals, all of them had its own energy level. And we drew them going up in energy because as we added nodes, this one has no nodes, this one has 1. And as we drew all of our diagram, none of those equal in energy because our nodes went up by 1. And there's only one way in each of these to draw one node to still have that symmetry. So we didn't have degenerate orbitals. And recall from general chemistry, yes, we still have to bring in general chemistry. Degenerate orbitals means orbitals that have the same energy level. Now with the cyclic system, however, we're going to have multiple ways we can put in a node and have a different orbital that looks different but has the same energy level. Meaning it has the same amount of good and bad interactions. Because that really affected our energy. The more bad interactions we had, meaning the more nodes, the higher the energy. But if we have multiple orbital drawings that have the same amount of good and bad interactions, then they have the same energy level. And that's a big difference, and that stems from the fact that our 6 unhybridized p orbitals are in a closed loop. They're not linear. So what the orbital diagram is going to look like for benzene is this. Our lowest orbital is still going to be the same. All of our p orbitals on the top are going to be shaded. All of our p orbitals are in the bottom are going to be unshaded. And our highest orbital is again going to be the same. We're going to have all up, down, up, down, up, down, up, down. But the difference comes in the middle ones. We still have a total of 6, but there's 2 different ways that we can have one node, and there's 2 different ways we can have 2 nodes. And based on that, that's why we have these degenerate orbitals. And these degenerate orbitals are going to be what explains the extra stability. So again, just like before, once we draw this, and you won't really have to draw these, because statistically it's a little hard for you to predict this, unless I give you a bonus with one, but you will have to draw what these look like. And I'll show you how to do that, it's really easy. And it's based on symmetry, it's really not hard to do. We know we started with 6 pi electrons, because we have 3 alternating double bonds, and each double bond has 2 electrons, so that's 6 pi electrons. So just like before, we have to fill it in. Now remember from general chemistry, when we're filling in degenerate orbitals, and this is going to be important for when we talk about other systems. So here's our benzene molecular orbital diagram. We're going to fill our lowest energy first, but then when we come to our degenerate orbitals, we fill unpaired before we pair. And that's really important for the discussion in this chapter. Benzene becomes completely full, but we're going to look at cases that don't, and what we call anti-aromatic compounds. So the fact that our 6p orbitals are in a closed ring system, meaning that we don't have an n-p orbital, is what causes our molecular orbital diagram to look like this. So for something to be aromatic, the first thing it's going to have to be is a closed conjugated pi system. If it's not a conjugated pi system in a ring, then it will not be aromatic. Because if it's not a closed system in a ring, we won't have this diagram. And this diagram is going to be important for aromaticity. So when we look at this diagram, this is our highest. We only have 3 nodes in our highest, but again, it's because it's cyclic. 1, 2, 3. That still results in the alternating up, down. But you only have 3 actual nodes. In our linear system, we have 6 nodes. So our amount of nodes is still 0, 1, 2, 3, just like in our linear system, but we only have 4 total energy levels. In our linear system, we have 6. So when we're completely full, what we have is 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. We don't have any non-bonding. Non-bonding would be equal amount of bad and good interactions. But that's not what we see here. Here we have no bad interactions. These have some bad interactions, but more good, so that's why they're a little bit higher. These have more bad than good, and these have completely bad. There's no sharing of electrons from our p orbitals in that highest level. And again, just like before, we can label this as our HOMO, our highest occupied molecular orbitals. Both of these are our HOMOs, because this is our same energy, they're degenerate, so they're both considered HOMO. And both of these are considered LUMOs, our lowest unoccupied molecular orbitals, because they are our lowest energy molecular orbitals that are not occupied. So again, same terminology. The fact that we have all 6 of our p orbitals that are in bonding orbitals and they're all paired is what contributes to our extra stability. It's really this system. Now you might wonder, why don't we consider our linear conjugated system aromatic? And to understand that, well, one, we don't see the same type of reactivity. If we take our linear system of 3 alternating double bonds and react with Br2, we will have an addition reaction. It will be a mess because of resonance, but we will have an addition reaction. So we do see normal reactivity with our linear system. So what makes this special? To look at that, let's compare the systems. So here is the diagrams we talked about from chapter 17. We've talked about them. Again, notice we increase in the amount of nodes going up and we don't have any degenerate orbitals. So we still have 6 pi electrons, just like here. And then here is our degenerate orbitals for our benzene. And here I'm not representing the actual p orbitals because, again, these two middle ones are kind of hard for you to visualize. You could probably figure it out, but I'm not really going to have you required to do that. But you will have drills. So if we fill in the orbitals, this is the difference. And as you can see, even though all 6 of these are in bonding orbitals, what we see is extra good interactions and extra bonding interactions with our benzene than with our hexatriene. And notice our highest occupied molecular orbital in our linear system is much higher energy than our highest occupied molecular orbital in our cyclic conjugated system benzene. So that's where we're getting our extra stability from. So whenever we fill a cyclic conjugated orbitals, and it has to be a full conjugated cyclic system, with 4n plus 2 pi electrons, meaning if we have an n where 4n plus 2 pi equals the amount of pi electrons we have, we're going to see this pattern of molecular orbital. So that's how we're going to figure out if we have aromatic compounds, by using that concept. And we can even draw out the orbitals to compare. And that's why our cyclic conjugated system has that special stability of aromaticity, whereas the linear system does not. And again, it has to do with the fact that being in the ring gives us these degenerate orbitals. And the linear system is not in a ring. Now, these are 2 other examples of fully conjugated systems, and the question is, every time that you have a fully conjugated cyclic system, is it aromatic? And the answer is no. It's actually not. These 2 compounds are very reactive. If we react them with Br2, they're going to react easily. In fact, this cyclobutadiene is so reactive that with a little bit of light present, it's going to react with itself to actually form cyclooxytrine. Because we have a lot of ring strain here, and the double bonds are not super stable. So why don't we see aromatic stability in all systems that are cyclic and conjugated? And again, to understand that, we can look at the molecular orbital diagram. So before that, I'm going to ask you this, because we're going to start looking at determining if something is aromatic or not. So there's 3 requirements for aromaticity, and technically requirements 1 and 3 are the same. 1, you have to have cyclic conjugation. If you don't have conjugation in a ring system, it is not going to be aromatic, because you will not have those degenerate orbitals, so you won't have that extra stability. So it has to be cyclic conjugated. That's where you get the degeneracy, that's what causes the extra stability. The second thing is it has to agree with Huckel's rule. Huckel is just someone. 4n plus 2 pi electrons. Meaning, benzene has 6 pi electrons. If I put this equation is there a whole number that I can fill in n that will equal 6 pi? There is. In this case, what is it? 1. 4 plus 2 equals 6. That agrees with Huckel's rule. The one we just looked at, cyclobutadiene, had 4 pi electrons. Is there a whole number I can put in n that'll give me 4? No. 0 would give me 2. 1 would give me 6. So cyclobutadiene does not agree with Huckel's rule. It actually agrees with 4 n pi electrons, which is our rule for what we're going to learn is anti-aromaticity. And we're going to look at that. And again, I'm going to explain why that rule is important with molecular orbital diagram. So we're not just going to be memorizing it, I will show you why only 4n plus 2 pi electrons makes it more stable. And the last rule is that the whole overall thing has to be planar. So if for some reason the ring, when it has its double bonds, cannot achieve being planar, it will not be aromatic. The reason why? You cannot have cyclic conjugation if you don't have planarity. The pi bonds have to be lined up. If they're not lined up, the electrons cannot be shared between the pi bonds. If you don't have the conjugation, then you don't have the molecular orbital diagram that we drew. That is dependent on the conjugation. So technically, Rule 3 and Rule 1 go together. You cannot have conjugation without being planar. But you could have a compound that's planar without cyclic. So the cyclic part of Rule 1 is what's really important. So that just makes sense. You can't have conjugation without planarity. The p orbitals have to overlap. So our electrons can be fully shared between all atoms of the ring. So looking at this one, why isn't this one aromatic? It does contain 4n plus 2 pi electrons. It has a total of 6 pi electrons in conjugation. There's 6 double bonds. And it may be planar, but it does not have a continuous cyclic system of p orbitals. This has a ring, but the p orbitals are not all in the ring. So this is just a linear system, and this one would look like the 6 p orbitals that we drew before. This is not a closed cyclic system of electrons. We don't have the same resonance that we have with benzene. So this is not aromatic. It's not part of a ring. If your pi bonds are not in a closed ring, it's not aromatic. Just as there's a ring there, our p orbitals are not part of the ring. This is sp3. This is sp3. This is sp3. This is sp3. What we would term this, non-aromatic. Technically, all compounds are non-aromatic if they are not aromatic or anti-aromatic. But we usually reserve them for labeling compounds that actually have double bonds. But technically, all compounds that aren't aromatic or aren't anti-aromatic, they're just what we consider non-aromatic. They're not aromatic. So this one isn't aromatic. It's non. That's what we would call it. So the answer for this one is D. It doesn't have a continuous cyclic system. It's probably planar. We might need to know more to know if it's a planar system, but it likely is because remember, conjugated double bonds are more stable if they're in conjugation. But we will see if we threw in Br2, this would react. So there are aromatic compounds other than benzene, and they can follow Huckel's rule. And again, that's at 4n plus 2 pi electrons. Or you might see this as an odd number of electron pairs. You will see that if you have an odd number of electron pairs, it will always agree with Huckel's rule. But if you just know Huckel's rule, that makes sense. And N can equal 0 if you have a closed loop of p orbitals. So a closed loop of electrons. So let's look at these two. Now these two don't agree with Huckel's rule. They may or may not be planar, and we'll actually talk about the fact that cyclooctatriene will oftentimes bend out of being planar, and there are reasons for that. But cyclobutadiene has to be planar. There's no way it can't be because of it just doesn't have it only has 4 carbons. It really can't bend too much. It doesn't have a lot of movement there. So cyclobutadiene has 4 pi electrons. There's no N. That's a whole number. N can't be a decimal place or a fraction. That would agree with 4 plus 2 pi. And here we have 8 total pi electrons. Now both of these are a closed loop of double bonds. Both of these are completely conjugated double bonds and everything. So this one has 8 pi electrons, and again, there's no way to solve that equation for 8 pi. There's no N there. So these two are both for sure not aromatic. We'll actually term them something else. But our benzene doesn't go. So that agrees with Huckel's rule. What's so special about the 4n plus 2 pi versus the cyclobutadiene and the cyclooctatriene? Let's look at them. So this is our molecular orbital diagram of benzene. And we already talked about the fact that all of our electrons are paired and in bonding systems. Now let's look at cyclobutadiene. Based on symmetry, this is what our molecular orbital looks like. And when we fill in those electrons, again, we're going to fill in the bottom two first. But remember, when we get to the deuterate, we do not pair them until they're full. So what occurs is our HOMO is a lot higher in energy, and in the HOMO, we have two unpaired electrons. And remember, our electrons want to be paired. So not only do we not have that extra good interaction like we do with our aromatic compounds, our compounds like cyclobutadiene are actually what we consider extra unstable. So while our aromatic compounds are extra stable, our compounds like cyclobutadiene are extra unstable. And if we look at cyclooctatriene, we're going to have, of course, we have 1, 2, 3, 4, 5, 6, 7, 8 unhybridized p orbitals. So we're going to have a total of 8 atomic molecular orbitals, but it's going to look very similar to our cyclobutadiene. And when we fill in 2, 4, 6, 8 pi electrons, again, we fill the bottom, then here, and again, what we're going to see is that our HOMO is again higher in energy and unpaired. So because of that, what we see is when we have a system that is cyclic and closed, and again, the molecular orbital diagram won't look like these unless if it's a cyclic conjugated closed ring system. So if this was linear, it wouldn't look like this, and it would clearly be non-aromatic. But we actually have a different terminology for compounds like cyclobutadiene and cyclooctatriene that are cyclic and conjugated with pi bonds, but does not agree with Huckel's rule. And that's called anti-aromatic. And anti just means it's the opposite of aromatic, and that's exactly what we see based on reactivity. This is much less reactive. This is much more reactive than you would expect a conjugated 4-pi system. So compounds that don't agree with 4n plus 2 pi, but do have that cyclic conjugated closed system are what we call anti-aromatic. And unlike our aromatic compounds, they're super reactive and super unstable. And again, it has to do with these. It all has to do with the HOMO. And it being unpaired and higher in energy. So how do you draw I'm going to show you how to draw these in a second. And if we compare that with our 1,3-butadiene in our linear system, what you see is, unlike our aromatic compounds, the anti-aromatic compounds are even more unstable than their linear systems. In the linear systems, all of our electrons are paired and our HOMO is lower in energy. But in the cyclic systems, when we don't agree with 4n plus 2 pi, it's actually extra unstable. Which again, anti means opposite from aromatic, and that makes sense. So there's two things that you're going to have to do. Well, three. You're going to label compounds as either aromatic, anti-aromatic, or non-aromatic. Anything that's not a cyclic conjugated pi system that's planar is going to be non-aromatic. But if you have a cyclic conjugated pi system that's planar, it could be either aromatic or anti-aromatic. So predicting what those look like is actually really easy. And it works because of symmetry and because our orbital diagrams is a mathematical process. So this is why it works. But you can use this trick. It's really easy. So you draw a circle, and then you take your ring, and you put your ring in the circle, and there's one thing that you have to remember. One point of the ring has to be pointed at the bottom of the circle. These will not work if you do not point your pointed ring down. So at least one carbon has to be pointed down. That's the only rule. Then you draw your orbitals where each carbon is, and that is your diagram. And then you fill in your electrons. That's going to work for any cyclic conjugated ring system. The reason why is because it's a symmetry thing. That's how it works. So if you actually were trying to look at the p orbitals and figure out symmetrically where the nodes would go, this would work. So that's why it works. But again, the key is, and you will draw this, I can give you any ring, and you should be able to draw this. The key is the point has to be pointed down. So, and remember, energy is always going up. Then you fill in however many pi electrons you have. Here is 4 to 10 membered rings, and you see that as long as it points down, the frost circles predict these. So you won't have to draw the actual p orbitals in the nodes, but you should be able to draw these. As you can see, this is the one we've been looking at with benzene, but you should be able to draw the molecular orbital diagram and put in the electrons for any cyclic conjugated ring system. But the key, one of the points have to be pointed down. If the point's not pointed down, then it's not correct. So I often see, even though I repeated this 4 times, I'll still see this drawn for a 5-membered ring, and this is not right because the point is not pointed down. The point has to be down. But then that's your molecular orbital diagram. And then you can explain aromaticity versus anti-aromaticity with this. And I will ask you to do that. So look at this example. We can see that again. And again, I'm just pointing one of the points down. Now, for something like this guy, because it's extra unstable when it's planar, oftentimes the cyclotetra octane will bend itself out of planarity because remember, the linear system would be more stable. So if it wasn't planar, typically conjugation will make a compound more stable. If it's not planar, it can't be in conjugation, and then it loses that anti-aromatic instability. So compounds like this that can will often bend out of plane because remember, our atom, our molecule isn't thinking about what it's doing. It just always exists in its lowest energy form. So typically it will exist in its lower energy form. So drawing it like this means it's not planar. So if this isn't planar, it's non-aromatic because we don't have that conjugation. So this is just a review. This is not a ring, so it's not aromatic. This is not a cyclic closed system because this is sp3, so it's non-aromatic. It's not continuous. And this is not planar, so it's non-aromatic. So you will be doing this. Now we're going to talk about compounds that, let's say, have charges or have other atoms other than carbon in the next couple of slides. Y'all have a good weekend. If y'all are going to Voodoo this weekend, be safe. Take an Uber. Don't get lost in the park. It gets really confusing after dark. It's a really big park. Watch where you're going. There are areas. You gotta be careful. And if you see me, just turn the other way and don't come talk. I'm not there. You never saw me there. Y'all have a good weekend.